All right. A few of you were absent yesterday. I want you to put a big star on slide number 35. You're probably going to see that little diagram again. So slide 35, this one. Let's do a quick review. Main characteristics. Haley, which type of wave is going to arrive first? The P waves or the S waves? The P waves, right? Because P means primary, they're going to be faster. So then, which waves are our slower ones, Aiden? So we have P waves and we have S waves. Which ones are going to be slower and arrive second?
I know.
The P waves or the S waves? Aiden?
Red nose.
Nope.
Right on.
Oh.
So listen to my hint. What is going to arrive slower and second? The P waves or the S waves?
S.
There we go. Hear those clues. Second, slow, right? What shape do the S waves also kind of make?
An S.
An S shape, right?
Yeah.
So they go up and down and up and down. And if you think of the letter S being turned kind of on its side, it looks like the shape of the waves that they form. Who remembers what these waves are called? These up and down S-shaped waves? They are the transverse. Very good. So what type of waves do the P waves move in? What is that called in this motion?
Compression.
The compression, right? They compress and then expand. They compress, expand. Can an S wave go through the outer core?
No.
Why?
It's a liquid.
Liquid, right? Cannot go through a liquid. Can a P wave go through the crust mantle and core?
Yeah.
Yes.
But
Okay.
it just slows down.
Good. So as you go into different layers, the densities are different, and so it changes the speed. Good. We talked about reflection and refraction yesterday. Which one means bounce? The energy, the image, the sound, whatever it is, gets bounced. Which one is that? Claire. A reflection. Think of like an echo. Think of like, even like your image gets bounced back to you. That's why you can see it, right? It's a reflection. So then what is the word for bend when something gets bent? Refraction. Very good. And that's where we see the waves get refracted. As they go into that more dense material, they slow way down. And then as they travel out of it, they'll speed back up. Okay? So yesterday I said my head would be like the epicenter, the origin of the earthquake. And then from there, if I put my hands down and make my little spirit fingers, what is that trying to show? All right, and what takes place or doesn't take place in that shadow zone area? Somebody that I have not heard from yet today.
Oh, dang it.
What does not take place there? What will you not find there?
Big sack.
Big knee.
Nye, what do you think?
The F waves?
There will be no S waves. That is one half of the correct answer.
Oh. I think I know.
Birthday boy.
Nothing. Like no waves will go through.
Absolutely. So no P waves and no S waves. So right here, this is the zone where if there's a seismograph station, you're getting nothing. They don't even know an earthquake is taking place anywhere, right? Anywhere else, you're gonna at least get some P or some S waves. So here you're getting P and S waves, right? Here you get nothing, and you can see that from the data that would be collected at any of those stations. And then the P wave, they're able to be exactly opposite, but you don't see any of the S waves because they got blocked from that outer core. Okay? So that's kind of where we left off yesterday.
The outer core is a bully.
It is a bully.
Yeah.
All right,
I'm
so make sure
small.
all of you have a star by slide number 35.
Yep.
You probably will see this again
I know, fix it.
at some point. Okay. And remember, with this shadow zone, no matter where the epicenter is, so it's not like these are the only place on Earth that would be in a shadow zone. If the earthquake started here, if I do my little weird analogy, my head is the epicenter, I put my hands down by my sides, that would translate to the shadow zone being down there. So it always just depends on, it's based off where does the epicenter begin, or where is it, and then from there, the shadow zone gets determined. Yes?
Do we ever have earthquakes in Ohio?
We can, when I was young, there was a real faint one. We didn't even know, like, we just heard about it on the news, it wasn't big enough that we really noticed. We'll look at a map next unit that kind of shows where the majority of people would experience earthquakes. Obviously California, but there are some other, seismic zones, and we'll take a look at those next unit though. So this is slide 36 where we're picking up today. So the amount of time that it takes for a seismic wave to pass through the earth and through its layers depends on the material, right? Because we know that if it's more dense, it's going to slow it down. Just like you running in water versus you running in air, the water is more dense, so it's going to slow you down. All right, so we talked about that. It's also going to have the potential to bend the path, right? And so at these seismograph station, we can monitor the arrival of the waves. And so then we can it helps us, or it has helped us to determine what's in the earth. Like, what are the layers, like how dense are they, what are they made of? Because we know how fast they should be traveling. And like we know, from collecting other data, we know a lot. So we can use that information. We're gonna kind of show you how. The one video we watched yesterday demonstrated this a little bit.
We're almost done.
We are.
Sorry.
All right, so these waves, we can kind of interpret graphically. So if they're collecting data from lots of different stations, they can track the path of the P wave and the S wave. Notice whenever you have a graph, you always look at the labels. So distance from the epicenter, it has the units of the kilometer, right? So you always want the label, and if there's units, make sure they're included. Here we see that everything over here is going to represent time, and the units are minutes. And it'd be nice if it had a title, but it doesn't. So that's something that's kind of missing. So we're going in, it looks like 2,000 kilometer intervals, right? 2,000, then there's 3, then 4, then 5, then 6. So I know that each space is going to be worth 1,000 kilometers. It looks like each space as I go up is going to be worth 2.5 minutes, right? Because we go 5 and then have another space and then 10. So it's always kind of nice to have that kind of in your mind before you start interpreting a graph. What is each space worth, right? So it says determine how many minutes it took for the P wave to travel 6,000 kilometers. So this is just using a graph. I go 6,000 kilometers
And it
wants
goes
the P
10.
wave. So I'm going to go up until I hit the line for the P wave, and then I'm going to go over. And so what is that,
10 minutes.
Jonna? How many minutes did it take for that P wave to travel 6,000 kilometers?
No.
So if we're at 6,000,
Sorry.
we go up to the blue line and then go over. There we go. 10 sounds good. All right, does everybody see where that's coming from? Because you're going to have to be able to do this. Aiden, you got it? You with me?
Go over. Oh, I know the next one.
6,000 kilometers till you hit the P wave line and then go over because it wants time in minutes. Okay?
That's the S wave.
All right, so then it says determine how far the S wave traveled after about 12 minutes. So now we're going to go to the minutes, that's what's given,
1,000.
until we hit the S line.
Wait, no.
So if we go, do that on yours and see what you're going to get. And again, this is going to be like, wow, bless you. It's not going to be exact.
Say it.
Brooke, what do you think?
3,000. Go, Brooke.
And it can be just an estimate, like what's it? 9,000. Okay, so if we go, let me see, make sure my pens are working.
Oh, let's go to Grady then.
Alright, so this would be like 12 and a half, because we said each space is worth 12. So if I'm just, or each space is worth 2.5, sorry. So if this would be 12 and a half, I'm gonna be just under this line. So from there, I'm gonna like kind of go like this. I hit my line and now I drop down. So what's that put me close to?
4,000.
What do you think?
Oh, 3,000. Yeah. I got an idea.
Brandon, what do you got?
4,000.
Pretty close to 4,000, so it's kind of between the 3,500 and the 4,000. Depending, and it's nice, you know, if you're dealing with paper, or you can draw on what you have in front of you, you know what I mean? Like, it's nice just to be able to do that. Go with what they give you to start with, right, which is your 12 minutes, and then from there, go to the line they tell you, and then from there, drop down to get your kilometers.
It's like
Alright, so, when it's not following lines exactly, you know, an estimate would be fine. If you had told me, you know, like it's approximately 4,000, that'd be fine. You have to be close. Like if you tell me it's 2,000, obviously that's too far away. 3,000 is probably a little far, and 4,000 is probably a little far. Just realizing that it's gonna be somewhere in the middle of 3,000 and 4,000.
Wouldn't it be close to 3,750?
Well, you could put that and that'd be fine. Again, we're not getting an exact answer because we're not, now like if we were exactly on the lines, like if we were at 15 and it dropped down and it was exactly right here, then you better tell me 5,000. But because you're in between, I would take anything that's kind of close to that. Okay? And really this is 3,000 and this is 4,000. So 3,500 would be the middle of that value. So 3,500 is fine. If you did 3,750, like I'm fine with that too. Okay, now there's something called the SP interval. What that means is how much time took place between when the P wave got there and when the S wave finally got there. Because think about it, the P wave is primary. It's going to arrive first. The S wave then follows along second. So something called the SP interval, you're just finding the two times, and then from there, you are, you know, figuring out, like, the difference between them, right? So, it says how many minutes pass between the PS waves at 4,000 kilometers. So I'm gonna make sure that I am looking at 4,000 right here and right here, okay? I'm going with what they've already given me. I'm looking at this distance,
okay, so
and from here puts me about there, and following this one across to my minutes puts me about here. So we said that each space was 2.5. So this is going to be 7.5, right? And then this is our 12.5. So like maybe 13. And again, this is where the estimate or just kind of, you know, a good guess comes in. So 13 minutes and 7.5 minutes. So to find how much passed, what are we going to use? What operation? Sarah? Yeah, we're going to subtract them. So if you take the slower one, subtract it from the faster one.
Oh, wait.
What are we going to get?
Don't answer me. I got this. 13.
5.5. All right, so if we have 5.5, and a way that I like to check it, and you'll always be allowed to use a calculator, but if we do 5.5 plus 7.5, we should get 13.
Yep.
Everybody like it?
That is so
All right, so it would be about 5.5, or again, when it's not exact, an about or an estimate is fine. So if you would have even just said 6, that's fine too. That's close enough. I'll tell you when things need to be exact. And again, it's hard to be super exact because you're like, well, you know, is that really 13? That's a pretty good estimate, but again, when it's not exactly on the line, that's when you have to make your best judgment call. Okay, so those are some things that could be asked, and most of the time it's just interpreting using a graph, like whatever information they give you. Use that to find the unknown. If they give you time, then you're going to use that to find the distance. So it can definitely, you know, again, it's just using a graph. So let's take a look at this one. Again, I'm looking at distance in kilometers, time traveled in minutes, and it says how long did it take the P wave to travel 5,000 kilometers. So I'd like you to try this one, right? So I want to see everybody try it. You have the graph on your paper.
Got it.
So we're looking at 5,000 kilometers, and we're looking at the P wave. And I know that your graphs are kind of faint and they're kind of small, but just kind of follow the process at least for sure.
I got it back with I can't see our graph. I think it's higher than that because look. I think it's 16.
All right, so what's it look like? What's gonna be our best estimate for how long this is gonna take? Time.
No, it's on. No, it's one above it. It's not? Yeah, look.
What do you have, Audrina?
It's different.
Okay, so again, you find the 5,000, go up to the line that it's telling you. Make sure if it's saying the S wave, go to the S wave line. If you're wants the P wave, make sure you go to the P wave. Right, so from there, I'm gonna go over, and it's about 8.
That's the left we only.
Good. All right, so now it says how long did it take the S wave to travel 5,000? So let's do that. So if you go 5,000, up, 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 now I go to my S, all right? And then from there,
15.
let's go over.
14.5.
What do you think, Aiden?
15.
Okay, so probably right in there in between, and again, because it's not exactly on a line, an about answer or an estimate is just fine. So we liked the 8 minutes for the first one, and maybe about 15 for the second one. All right, so which one traveled faster?
The P waves.
Do we even need the graph to answer that?
No.
No, right? They always travel faster. They're the primary ones. So even if you didn't know, like if you were having trouble looking at that on the graph, you already know this. We don't even need the graph. But if somebody ran a race in 8 minutes and somebody ran a race in 15 minutes, who was faster? The 8 minutes, right? So you could use the graph to answer this, but you guys are already so smart that you know, P waves are always getting there first anyways.
I am the P waves. It's so low.
All right, here's just another, way to kind of show. So we know that as the waves travel, the density changes as they go through those different layers. And because of that, we get drastic slowdowns. So here is the speed of the seismic waves right here. This is the depth, and I think that this little box is covering up, it's probably in kilometers would be my guess. It would have been nicer if we had a nice layer, or a label down here. So like depths in kilometers. That label is missing and the units are missing. So if you had made this graph, that would be a problem, right? So sometimes it's nice, like just to identify if there's something off or there's an error with something that we're using. Here they should have had a label and they don't, right? So you can see it's, you know, the speed is increasing, and then it changes as it hits that MOHO boundary. And then you can see it's speeding up, and then bam, it slows way down. And if we do the same thing with the P waves, it's speeding up, it hits that boundary, and then it speeds up again as it starts to go through the mantle, and then all of a sudden, bam, it slows way down again, right? And then look what happens to the S wave. Does it come back? No, it goes away. What layer do you think that is? Probably hits the outer core, right? The P wave was able to go through, but the S wave was stopped. So this is another way. So if we're looking at the first layer, we're probably looking at it going through the mantle here, right? Because the crust, then we had that little MOHO boundary, and then we know that we know the S waves can go through mantle, and so they get stopped at our second layer, which would be the outer core, and then finally that would be our inner core. And so when the S wave goes away, then we know we've reached the outer core, right? So this is just another way that a graph could be used to kind of show what's going on, what layers you're in. All right, oh, I need to erase those. Erase them. All right, so a seismic profile looks kind of like this, and it showed this in the video yesterday. It's also a way that this information can then be kind of turned into a graph. And so this information is kind of like the raw data, I guess you could say. And so these seismic waves travel in something called two-way time, or TWT. And two-way time represents how long it takes a surface-generated seismic wave to reach a rock layer and then return to the surface. So we're looking at the bounce, which is what again? Is that refraction or reflection?
Reflection.
Good, the bounce is reflection. So if this is the source, it sends a signal, and then it gets bounced and picked up by this receiver. And then maybe a stronger wave is sent through, and it goes even farther and then bounces back. Same thing. This information is represented in this raw data, and then it gets transferred into this. Because we know how fast the wave should move. We know we can record the time it takes to receive each of these bounce back waves. Ooh, sorry, thanks. And because of that, the equation for speed is distance divided by time. So if we know the speed and we know the time, we can calculate the distance. You can rearrange that equation to calculate distance. And so that's how they're able to know like what these layers are, because if there wasn't a change in layer, the wave would all come back at the same time, and it doesn't. It comes back in 3 or 4 or multiple different times. And so from that, they're able to calculate, okay, what went through another layer as it took longer for it to come back, right? So you're not gonna have to do that. I just try to explain a little like where some of this information comes from. And then there's one last thing for this unit, and it is called triangulation. How many things do you think are gonna be involved in something using triangulation, Audrey? Probably 3. Like a tricycle has 3 wheels, a triangle has 3 sides. Tri means 3. Okay? So,
like triangles.
we know that the seismograph stations, and so Zach, you had said something, is it kind of like paper with like a little pen squiggling? So this is kind of what, are at some of these seismograph stations. And so you have these big reels of paper, and they probably are a little bit more high tech now, I'm assuming. This is kind of an older image, but this is where the data would get collected.
Whoa.
Okay? And triangulation is going to use data from 3 seismic stations, right? You have to have data. You can narrow it down with 1. You can get a little bit more specific with 2, but to pinpoint exactly where an earthquake originated from, you have to have 3 stations. Has anybody watched like crime or like cop shows at all? So they're searching for the perp, and they're like, we have to triangulate his location, you know, from the 3rd cell phone tower. They can't narrow it down. Have you ever heard them say that? Triangulation, ping it off of the cell phone tower. No? Never? Oh, what are you guys watching these days? So I watch a lot of shows like The Blacklist, and like, I like those kind of like cop mystery kind of things.
I watched CSI Miami.
Okay, so maybe if you might have heard this if you were paying attention, but they, you know, our cell phones ping off the towers. And so if a cell phone is pinging off of multiple towers, they can help pinpoint not just how far away are you from that tower, but if you have a second tower that your cell phone or your device is pinging off of or sending a signal from, then they can narrow it down even more. And if they would have 3 towers that are picking up the signal, then you could pinpoint a location exactly. And so the same process that they use for trying to track somebody, we use for trying to track where an earthquake started from. All right. So if we have Charleston, South Carolina, we have a seismograph station that's picking up data, and the data it got is saying that it is, let's say, 500 miles away. All right, so from 500 miles away, you can make a circle, and you know that that earthquake had to start somewhere on that blue circle. And then Detroit picks up data, and from their seismograph station, they can calculate in that 2-way time how far away the earthquake started from them. So let's say maybe this is 200 miles. So we have 500 miles, we have 200 miles. So they make a circle, and anywhere on that red circle is going to show.
I get it now.
Okay, good. That's awesome. You were like so excited. Yeah.
Where they all cross is where it starts.
Where they intersect is the actual origin.
That is so
because it has to be where all 3 of them. So look, they cross here also, just 2 of them. So, but that's not really going to be very helpful. Like, let's go back to the person. Let's say you're trying to track somebody. They could be all the way over here in, what did that be? Indiana, Illinois, right in the bottom of there. Or it could be all the way over here on the East Coast. At least you have it narrowed down to those 2 spots, not these 2 big circles. But if we could have one more piece of data, that would get us there. And so when Minneapolis picks up their seismic information and they can calculate the distance, it's represented with the green circle.
Right there.
And the only place where all 3 circles intersect is right there. Yes.
From where I am, it looks like they intersect a 3rd time. Yes, another time, all 3 of them.
No, we don't. Stop. 6 minutes.
I see there. There's 2 there. There's multiple places where 2 of them intersect, but not all 3. They only all 3 intersect one place. Just one. Okay, let's.
Nope.